Welcome to the low pass filter experiment. In this experiment, we will be looking at a passive low pass filter. This passive low pass filter is of the RC configuration, which means resistor and capacitor in series and in parallel to the output. So if you can observe, the resistor is connected in series with the input, and then the capacitor is connected in parallel to the output. This resistor is 1.5 kilo ohms, which is a standard E6 series value, and this capacitor is 100 nanofarads, which again is a standard E6 value. We have placed it into the breadboard. Next, we will hook it up to the equipment. So first thing first, we have to hook up the function generator to the input of the circuit. So we will use a BNC to alligator clip. So this is BNC on one side, this goes to the function generator, and then it has two alligator clips on the other side. This will go to the input of the circuit. So we will connect this BNC onto the first channel of the function generator, and then we will take two wires, two DuPont cables to connect our circuit. So one DuPont wire I will put on column number 10, which is the left leg of the resistor. One side I will put down to ground, which is the ground rail on the breadboard. So we take the black wire connected to the ground rail of the breadboard, and I'll use another wire to do that. Then next, the leg of the capacitor has to be connected down to ground. Since it is in column number 20, I'll put the DuPont wire in column number 20 and take it down to ground. So now the connections are as follows. The first channel of the oscilloscope is connected through a BNC cable to an alligator converter connecting to ground as well as to the input of the circuit. The input of the circuit being the left side of the resistor. So the right side of the resistor is connected to the leg of the capacitor. This is a non-polarized capacitor, so which does not matter which side is connected to what. So the top of the capacitor is connected to the right leg of the resistor, and the bottom of the capacitor is connected down to ground. And the ground is connected to the ground of the function generator, and the positive of the function generator is connected to the left side of the resistor, as I said. Next up, we have to connect the oscilloscopes. So you're going to be using one 4-channel oscilloscope. So the first thing we will do is connect the ground of the oscilloscope to the ground of the circuit. So we'll take the ground clip of the oscilloscope probe, connect it with the DuPont cable, and then connect it down to ground. Then I will take the probe and I will place it in the left side of the resistor such that it is able to measure the input voltage. I will just press it down into the breadboard. As so. And then I will take the second oscilloscope probe and place it on the right side of the capacitor or the right side of the resistor. So that is the output of the circuit. So now the connections are as follows. The left side of the resistor is connected to the input of the circuit, which is connected to the output of the function generator, which is also connected to the first channel of the oscilloscope. The right side of the resistor is connected to the capacitor, which is also connected to the output of the circuit, which is going to the second channel of the oscilloscope. Now we will look at the waveforms. So we will feed a sine wave into the circuit and we will look at the waveforms. So I will give a voltage of 1 volts. So sinusoidal waveform, and then voltage I will set to 1 volts. Amplitude is 1 volts. I will turn the function generator on, and then I will adjust the oscilloscope so the voltage is visible. I'll go to channel number 1, adjust the volts per division. I'll adjust the time base as well. So the yellow is the waveform of the input, and then the pink or purple is the output. As you can see, the purple waveform is smaller than the yellow waveform. So we'll start at 1 kilohertz and we'll take the measurements. So I will go to measurements. I will put type as for channel 1. So type as peak to peak as well as frequency. And then channel 2 I will measure peak to peak. If you want, we can also measure the current waveform. So if I just put the scope probe current lamp like that and adjust channel 3 to the smallest division, we can check. The current is too small to measure, so we will just ignore channel 3 for now. And we will focus on channel 1 and channel 2. As you can observe, the waveform also has a phase shift. Let's also measure the phase shift. So let me zoom onto the oscilloscope first of all. So now on the oscilloscope screen, we can adjust the oscilloscope such that it can also measure the phase shift between the two. So we will go to measurement, we will go to type, and we will do channel 1, channel 2, we will do phase measurement. So now the phase shift we can also measure. The phase shift being 40, okay, we will start at 100 Hertz. So I'll set the frequency to 100 Hertz. We'll start at 10 Hertz. So we have to readjust the horizontal scale so we can measure a slowed frequency. So both of the voltages are exactly in phase. The phase shift being 0. It's negligible. So the phase shift at 10 Hertz is negligible. The input voltage is the same as the output voltage because it is exactly overlapping. So let me 1 second turn on channel 3, go to measurements, type, disable the measurement. And go to channel 1 and then type as peak to peak. And then just disable channel 3. Let me go to acquire and then disable the averaging, and let's continue. So as you can observe, the oscilloscope is able to measure the input voltage, output voltage, as well as the phase shift. So The phase shift between the two waveforms is 0 degrees. The frequency is 10 Hz and the peak-to-peak voltage at the input is 1.0 and the output is 1.1. So it is roughly the same. Because of little bit of noise present on the waveform, the voltage appears to be slightly higher. So then let's move on to 100 Hz. So I will enter 100 Hz into the function generator. And when I press enter, it will shift it. So now we have to zoom into the waveform again to see the result. So as you can see, a little bit of noise is present, so I will just do some erase on the acquired setting. So we get rid of the noise. So enhance it by 2 bits. Okay, that got rid of a lot of the noise. So now the small amount of phase shift has developed. The phase shift being about 5 degrees. Frequency is 100 Hz. The output voltage is basically the same as input voltage. Input voltage being 992, output voltage being 992 millivolts as well. So being a low pass filter, it will allow low frequencies to pass just fine. So next we will move on to 200 Hz. So I will just adjust it to 200. At 200 Hz, the phase shift has doubled into 10 degrees. The voltage is still 992 millivolts and 976 millivolts. So the voltage has started to drop. Going to 500 Hz and zooming in again for higher resolution. Now the phase shift has increased to 25 degrees. So now the impedance of the capacitor is starting to impact the performance of the circuit, as the capacitor's impedance is decreasing with the frequency. Now the voltage at the input is still roughly 1 volts, and then the output voltage has dropped to 960 millivolts. Then let's move on to 1 kilohertz. 1 kilohertz is the minus 3 dB point for this circuit. So at the minus 3 dB point, it should be 770 millivolts because the input is 1 volts. So the phase shift has now risen to 43 degrees. The frequency is 1 kilohertz. The peak-to-peak voltage at the input is 992 or 1 volts roughly speaking, neglecting the noise, and the output voltage has become 780. So this is the minus 3 dB point. Basically the minus 3 dB point is the point at which the power becomes half. The power will become half at 770 millivolts. So because we are measuring about 780 millivolts, we have reached the minus 3 dB point roughly speaking. This is at 1 kilohertz. Let's move on to 2 kilohertz. At 2 kilohertz, you can observe the voltage has significantly dropped. So if you measure the phase shift as well, it is also much higher. So the phase shift has now become 62 degrees. The frequency is 2 kilohertz. The peak-to-peak voltage is 1 volts at the input as it should be, and the output voltage has dropped to 580 millivolts. So 0.58 volts is the output voltage. Now let's move on to 3 kilohertz. At 3 kilohertz, the phase shift has increased to 72 degrees. The output voltage has dropped to 450, 460, something like that. So moving on to 5 kilohertz, we can observe the voltage is dropping continuously as this is a low pass filter. So the phase shift, if you want to measure, it is about 81 degrees now. At 5 kilohertz, the output voltage has dropped to 320 millivolts. So it is continuously dropping. Eventually there will be a point where the voltage completely diminishes. So moving on to, let's say, 10 kilohertz. Again, the voltage is quite diminished now. The frequency being 10 kilohertz, it is having a difficult time measuring the phase shift due to the noise. So what we will do is we will go to acquire and do averaging. So instead of ERAS, we will do average. Average, we will do about 16 averages. That gets rid of the noise, and now the phase shift is about 88 degrees. 88 degrees phase shift with an output voltage of about 120 millivolts. So the voltage is basically diminished now. So let's move on to 20 kilohertz and see the voltage diminish almost completely. Because of averaging, there is some artifacting. So just ignore the artifacts for now. At 20 kilohertz, the voltage is starting to disappear and the phase shift is about 95 degrees, 96 degrees. the voltage has become 72 millivolts. So at this point, we have to zoom into the voltage, but we can stop the experiment here. So as you observe, the low pass filter is allowing the low frequencies to pass just fine, but it is not allowing the high frequencies to pass. As we increase the frequency higher and higher, above the minus 3 dB point, the voltage starts to diminish. This is a single order filter. Single order filter means it has one set of capacitor and resistor. This single order filter has a slow slope. The slow slope basically means the voltage diminishes at a slow rate. As we move from 1, 2, 3, 4, 5 to 20 kilohertz, the voltage will not drop that rapidly, being a single order filter. If you want the voltage to drop more rapidly, we have to go for a second, third, fourth, fifth, or even ninth order filter. That is it for this experiment, and we will conclude. So let's continue on with the high pass filter. The high pass filter differentiates itself from the low pass filter by only the position of the component. The capacitor and resistors have been swapped. As I said, this relies on the voltage divider principle. The capacitor and resistor form a voltage divider. The capacitor is frequency dependent. So as the capacitor value changes, the resistor divider voltage will shift. The capacitor impedance is inversely proportional to the frequency. So as the capacitor's impedance depends on the frequency, as we increase the frequency, the impedance drops lower and lower. So basically what happens is that most of the voltage drops across the capacitor at low frequencies. So the voltage in parallel to the resistor, which is our output, drops a small amount of voltage, resulting in a small amount of voltage to be present at the output. As we increase the frequency, the impedance of the capacitor starts to drop. So now what happens is that less and less voltage drops across the capacitor, which is being wasted, and then more and more voltage drops across the resistor. Because the resistor is in parallel with our output, the voltage that we observe at the output starts to increase. So the increase in its frequency causes an increase in output voltage at the resistor. As I said, because the resistor is in parallel with the output. So there will be a point where the impedance of the capacitor is so low that all of the voltage drops across the resistor. That is after we cross the minus 3 dB point. So what we will do is we will run the experiment and see how the capacitor causes the impedance to change and how the voltage divider causes the voltage to shift. So we will start at 20 kilohertz and we will go downwards in descending order. So now let's continue with the experiment. Starting at 20 kilohertz. At 20 kilohertz, you can observe the voltages are basically on top of each other. So let's start at 20 kilohertz. At 20 kilohertz, as you can observe, the voltage is basically the same at the input and the output. The phase shift between the two voltages is negligible. It appears to be about 3 degrees, but the 3 degrees is quite small. We can neglect it. The frequency that we have is 20 kilohertz. As I said, we will be going in descending order from high frequencies to lower frequencies, and we will observe the voltage dropping off. The peak-to-peak voltage at the input is 1 volts and the peak-to-peak voltage at the output is also 1 volt. So let's go on by changing the voltage down to 10 kilohertz. As we are using averaging, there is a small amount of delay before the voltage appears and there is some artifacting present. So let's zoom into the voltage and measure the phase shift. The phase shift has increased to about 6 degrees as we are approaching the minus 3 dB point. The frequency is 10 kilohertz. The input voltage is the same at 1 volt peak to peak. Output voltage is also 1 volt peak to peak because the minus 3 dB point is at 1 kilohertz. So we are still quite a bit away from that. So let's drop down to 5 kilohertz. At 5 kilohertz, the voltage will start to shift. So the phase shift that we have developed is now about 11 degrees. 11 degrees of phase shift at 5 kilohertz, and the output voltage has also started to drop. It is 952 now. So that is a small decrease in the voltage. So if we go down to 3 kilohertz, you'll observe the voltage drop further and the phase shift further increase. So now the phase shift has increased to about 17 degrees, and the peak to peak voltage is 920 millivolts. So 920 millivolts at the output. So let's drop down to 2 kilohertz and let it settle after the averaging. So now the phase shift has increased to 27 degrees and the voltage at the output is 864 millivolts. So the voltage has started to drop as we are approaching the minus 3 dB point. At the minus 3 dB point, the voltage is supposed to be about 770 millivolts. So let's see at 1 kilohertz whether we get 770 millivolts or not. So at 1 kilohertz, the phase shift has changed to 46 degrees, and then the voltage has dropped to 680 millivolts. So the voltage is less than what we expect. So the minus 3 dB point is just above the 1 kilohertz mark. So let's drop the frequency down further and let's go to 500 hertz. And let me adjust the time base again. And now we can observe that the phase shift started to increase significantly as the capacitor's impedance is starting to counteract the flow of voltage. Now the phase shift has increased to 64 degrees with the output voltage being 432 millivolts. Now the voltage has significantly dropped. As this is a high pass filter, it will allow all of the higher frequencies to pass above 1 kilohertz quite easily, and then as we go lower and lower from 1 kilohertz, the voltage will drop significantly. As we can observe, the voltage has dropped quite significantly. And let's move on to 200 hertz. And let me adjust the time base again. And let the noise cancel out by averaging. And now at 200 hertz, the phase shift has increased to 77 degrees with the output voltage dropping all the way down to 192 millivolts. The input voltage is still roughly the same at 1 volt peak to peak, so we don't have to worry about that much at all. The input impedance of the circuit does not shift by much, but the output is where the impedance change happens across the capacitor, and then that causes the voltage to develop across the resistor to change. As we drop in frequency, the impedance of the capacitor becomes higher and higher, so more and more voltage drops across the capacitor, effectively wasting it. And then the voltage that drops across the resistor, which is parallel to our output, is less and less. Moving down to 100 hertz, at this point we should see the voltage diminish quite rapidly. Now the voltage is roughly dropped down to 104 millivolts and the phase shift is about 80 degrees. Let's drop the frequency down to 50 hertz and see what happens. Dropping the frequency down to 50 hertz, you can see the voltage is starting to disappear completely because the voltage has become so diminished. The phase shift at the moment is about, let it settle, about 80 degrees. Then the voltage at the output has dropped all the way down to 56 millivolts. It came from 1000 millivolts all the way down to 56 millivolts. So it is quite a difference. And dropping down all the way to 10 hertz, let's see if the voltage completely disappears. It will take a couple of seconds to settle, and let me adjust the time base. 10 hertz is quite slow, so it will take a couple of readings for it to settle. We are using averaging of the oscilloscope to cancel out noise, so we can observe the small voltages more easily. Yes, we can zoom in, but for the sake of consistency, we will keep the zoom at the same level. So now the voltage is so small, it is not able to measure the phase shift. And the voltage has dropped down all the way into the noise floor. So noise floor is basically where the oscilloscope is not able to accurately measure the voltage. So the voltage has basically diminished at 10 hertz. This being a high pass filter, this is completely expected behavior. So that is it for the experiment, and we will conclude.